Recording.
All right, good morning. This is the last Aviate seminar, and we're going to present some of the developments regarding TC4. Uh, we have been responsible on developing capabilities for testing, simulation, and field testing, a type of capabilities. So uh, here's an outline of the uh, what we'll try to do today. So I'll say a few words about the demo meeting in Reno in about a couple of weeks. That will not last long, and then I'll let the main uh, developers of our TC, which is Hyunjin and Christos, to present some of their works, and that should be it. So, regarding the demonstration meeting, that will be May 28 and 29, and at Reno, University of Nevada, Reno. So it's going to be the Joe Crowley Student Union Center, and that is inside the main UNR campus. And this is sort of a picture of how it looks. It's a very nice, new, relatively building, and has lots of facilities there. So, and there will be also the demos, the field testing, which will be at the FAA approved sites, one being at Silver Lake, which is about 30 minutes away from Reno, and the other would be at Doyle in California, which is roughly 45, 50 minutes from Reno. Um, so Doyle would be the place for Sierra Nevada Corporation to show us their vehicle and demonstrate there. Here is a rough agenda, which will be posted soon, and we'll be changing that, of course, based on the needs. But primarily, we're going to have maybe a 2-hour early morning session where we would be presenting pretty much the what we are expected to see at the demonstration. So explain the demonstrations. Then we will go to the demonstration sites from 9:30 all the way to about 1:30. Uh, the first day, we plan to have 2 demonstrations. One would be a Christos demonstration of the amphibious vehicle, and also then go from the Silver Lake to Doyle to have SNC show us their vehicle and demonstrate there. And so the window from 9:30 to 1:30 would be devoted to demonstrations. Then we will get back. So in the middle, we can have some box lunches served. And then in the afternoon, we will have about 3 to 4 hours of presentations, and then dinner. And the second day, which would be Thursday, May 29th, would be pretty much similar. Similar. We're going to have the demonstration of the covariant steering, and then back to UNR for more presentations and discussions. So that's pretty much the schedule. And as I said, we will put everything on the website. And the website is you can you have the link. You can go there and see what's going on, and the agenda might be changing depending on the needs. So if you have special requirements, I sent you an email to let me know. I got some responses, so we are trying to accommodate everything. And obviously, we're looking forward to have you here in about 2 weeks. So with that, I'd like to pass it to Hyunjin and talk about his works on the development of the simulation. So if you have any questions for me now or later, let me know.
Okay, let me share.
Petros, Irene typed a message about guest parking, so make sure when you negotiate a few slots for bagging or what.
Yeah, we will take care of that. Yeah.
Okay, good morning. So here at Tennessee Tech, I've been working on the simulation, and also here I'm also developing a VTOL vehicle. This was our vision when we wrote this proposal years ago. Looking at this, Back to the Future, that is a classic movie, and I was really fascinated about this. Our focus at Tennessee Tech is developing the simulation environment that can get high fidelity visuals for machine learning component. So and also you can support this real-time sensor and control loop integration. In addition to developing the simulation environment, also in addition to what Dr. Papacristo already has, we are trying to build bigger RC planes so that it can support relatively bigger GPU because it can be used for onboard AI inference. I think that can be essential for truly autonomous landing in urban environment. Simulation environment, this video is already presented in last meetings. Let me give you a very brief overview on this. So we have this VTOL vehicle that I downloaded from some computer graphic web store, and then I integrated this into Unreal 4 environment. And then we are building everything based on this Kala that is developed for autonomous car driving development simulator. So it is very convenient to have all the sensors set up. And then vehicle dynamics is calculated by NASA's Guam model. And then this video demonstrates that using very simple object detector like YOLO, you can detect a landing spot. And then using the error from the center of the camera view to the bounding box of the landing spot, you can actually guide the vehicle to land. You have seen this already, so let me move on to, and furthermore, not only that vehicle, but also we imported this Dr. Papacristo's Mini Hawk into this environment so that they can be tested within this Unreal game engine. So this is what we already have. More recent development is Kala finally released their Unreal 5 version of the simulation environment. So I migrated the vehicle model to this new UE5 simulation environment. And this new environment is already shared to by Ashik from our group to Ayush in Dr. Shah's group and Mikhail in Dr. Hobakin's group through Docker Hub. So because it is a Docker container and Docker images, so you don't have to worry about installing all that dependencies, but simply use a Docker. And to show you how it's better than Unreal 4, I got screenshot videos from the environment. In this environment, I added multiple helipad on the street, multiple place there, and also using this, you can get working traffic I've been envisioning that maybe if we can develop really good machine learning model and path planning, then we should be able to land at the intersection. So that was the idea. And this one shows the VTOL that I added, although this is running like a car mode at this moment, but all the sensor data is already being published to ROS data network. And I think that Mikhail in Dr. Hobakian's group and Ayush in Professor Lucia's group, they are further developing into our Docker distribution of simulation environment. I think that they're going to present on this simulator at Vino in demo days. Okay, let me introduce you the other activity that I'm doing. So I've been developing bigger VTOL that, according to what is written in the box of this RC plane, he said that it has 3 kilogram payload that include actually batteries. But still, it is a lot as a RC plane. It is believable because its wingspan is of 2.4 meters. If you look for UAV with wingspan about 2.4 meters, their price tag is usually between 10,000 or 20,000, even if they are made from China. But this is the base platform costs about, I think, $500, and Ori Nano costs about $500. And if we can use a very cheap the copycat of the Pixhawk autopilot, then I think we can build entire things within $2,000. That's what I think that this very first one is a very cheap material and cheap propellers, but I was able to hover it with large vibration. So and then I found that the issue was because the wing is very flexible. It's made of the styrofoam. Of course, it has the carbon fiber already reinforcement beam inside, but I think that I need to add more stiffness to the frame. So we work on that, and also the avionic carrier, although it has a large space inside, it's very hard to put the avionic device inside there. So we've been working and to improve the quality of vehicle. And I personally did CAD design because back then I did not have the graduate student and also undergraduate student to work with to show you what is inside. Here you can see a battery, and I can use this space for placing this Jetson Ori Nano Super. And here is a place for antenna and GPS antennas. And this Pixhawk 1 is mounted right here. And I added some power distribution board after this Pixhawk flight controller. As you can see here, we still have some space here and there. And I did not put the cameras yet, but we have enough space for accommodating even more electronics. And then to show you its capability of this Ori Nano Super. So Ori Nano Super is actually same hardware as Ori Nano, but they optimize their OS, so it can run on higher power. And then I tested with ground vehicle. And then here what you see is all the coast map and also the 3D voxels came out of MD-Blocks. MD-Blocks is actually GPU accelerated version of the existing 3D voxel map building developed years ago, but the NVIDIA optimized this so that it can use GPU. So I believe that it runs faster. With this NVIDIA Isaac ROS. Isaac ROS is basically GPU accelerated extension of ROS2. ROS2 has many packages. For example, it has a visual inertial odometry, and it has this MV Plus. NAV2 is fully capable of 2D navigation, and NAV2 has this global path planning that use something like A-star-like algorithm, and also it does have local planning and control. It was interesting that this distribution by NVIDIA Isaac Ross is actually using. It has two options. MPPI is one of the options. It is the other option that I do not remember, but I'm more familiar with MPPI because this is Evangelist's work. It was available with this NVIDIA Isaac distribution. So if you want to take a look at the map building that I got from my RC car with the same hardware that I mounted on this RC vehicle is pretty capable. But still, this computer is small. One caveat is this: the updating frequency of this inertial odometry is sometimes not fast enough. So if you make very sharp turn, then it seems to lose tracking. But it's still capable to build a map if you drive this RC car smoothly. And this is actually aligned with my interest. Looks like when we want to use limited resource in computation on board in this vehicle, right? And then clearly there's the need for resource allocation optimization. For example, when maybe vehicle is moving very fast or rotating fast, then maybe resources need to be put more on, I think, for example, visual inertial odometry so that it does not lose the tracks, rather than building this box maps. So I think it gave us interesting research motivation, and I think that's probably the purpose of all this tests actually. To show how it can be mounted, as you can see here, this place is safe for the camera, and then the battery is already placed inside of this fuselage, and this is NVIDIA Ring Nano. I did not connect the cable yet, but and the antennas are here. With this cover, there's still some opening, but I think I can fill this opening later if it's necessary. And meanwhile, in addition to developing this ML and robotic implementation or incorporation into Ori Nano on board, we are working on real flight development here at Tennessee next to the cows moving. But it is not flying very well yet. But I flew with this cheaper version of the vehicle already with large oscillation. So hopefully we get this flying well by end of this summer. That's my goal. The last part of my presentation is one of the use case of this simulation environment. It was presented in the recent SciTech. The author of this work is my two graduate students. In short, what we are doing, the motivation is, I think that if we want to use ready-to-use object detector or object detector trained with images that are collected from the internet, I don't think that they are best suitable for various operating situation with a vehicle. For example, here you can see it can be used for both daylight or dark night condition. Right? Let me skip this video. So you have pre-trained model, and then I can deploy this model and get system performance, right? And then what I can do is I can make decisions on the scaling or changing brightness or retraining of the model. And then I can use this retrained model in the simulator and get the system performance evaluation. Once again, this will give me new data point in this Bayesian inference, the performance, functional mapping, So if you go through this loop or iteration of the retraining, then actually you can improve the performance as we evaluate, and hopefully I want to deploy this with the real vehicle that we have. Now on this, show you the result. Before optimization, you see that in the simulation, out of 10 auto landing attempt, only 50% was success. With the training, now I was able to improve this to 70% from the 50%. So this is all the very preliminary, but this tell you that this simulator can be used for generating retraining data, or in other words, data augmentation to update the model. This is a very small problem for entire data exploration. I would say what we are not seeing, because of this training is treating the data as so one entire flight episode is treated as one data sample. That doesn't sound very efficient, because if we can have good state estimator, that will give us to break down this entire flight into each state transition, and then probably if I can use each state transition as individual samples for the training. That's our future goal with the students, but I think we have some start for fully developed data exploration. Okay, this is all I have. This introduced me and my two grad students, and especially this summer, I'm going to work with this two exchange students from the South Korea. That's my home country, and they are going to helping me drawing CAD and building 3D parts over summer. Thank you. This is all I have. Do you have any question? No, probably not.
I have a couple of detailed questions. Thank you. Very interesting presentation. So have you looked at this Qualcomm voxel computer? Do you have any experience with it with your aerial vehicles?
No, sorry. Maybe Christos knows better than this. It sounds interesting. Is it calculating for voxel mainly? Or?
No. It's just a computing platform. I'll send you a link to this. Just out of curiosity, how it would be interesting to see how this. I don't think it's comparable to the Orin Nano, but it'll be interesting to see how it's lighter. That could be useful for some of these platforms that you are building. Okay, and then the other thing I was wondering is this landing. So you're detecting the landing pad as an object, and then from that, are you doing some sort of pose estimation to figure out what the control input should be?
It doesn't do any pose estimation yet, but the NVIDIA Isaac Ross, they have fully developed the pose estimation using computer vision and IMU. So I hope to use this soon, but I did not do pose estimation yet. But if it is just running on the simulation, I can run this NVIDIA Isaac Ross visual inertial odometry on fast computer, the workstation. It's really possible, doable. I didn't do that yet, but I'm looking forward to use it sooner or later. So answer to your question is no, we didn't use it post estimation yet.
A quick follow-up. So at some point you were developing the simulation framework with Carla, right?
Yes.
And is this still related to Isaac Ross, or this is a completely different framework?
It's a different framework, but NVIDIA has something called Isaac Sim. But even if you're using Isaac Sim, the data will be published through ROS. So as long as I connect this color to ROS, then I can reuse all the tool developed by NVIDIA in Isaac ROS.
Okay. So are you pivoting towards Isaac Sim from away from Carla? Any I'm interested in simulation. We are doing a lot of simulation in our group as well. So anything we can learn from you about pros and cons of Isaac Sim?
I could be wrong because I'm also one of the explorer here, but
Okay.
Isaac Sim seemed to be good for like warehouse or small environment because that's they develop those assets mostly. But in contrast to warehouse, the game community, they're interested in to have the large space, at least good looking space. So that's why I think that Isaac Sim is at this point not very suitable for aerial vehicle, but I could be wrong because they're developing this very in fast pace. NVIDIA seemingly moving forward very fast. Yeah.
Thank you.
Thank you.
Okay, well, maybe Christos can pick up.
All right. Let me start the share from my side. Thank you, Eugene, and thank you, Petros. Can you see my screen?
Yes, I see it.
Yeah.
Great, thanks so much. All right, so thank you for the opportunity. The goal for today's presentation is to give you an idea of the kinds of systems and field tests that you'll be witnessing when you come over here to our demo day, demo couple of days at UNR. So without more further ado, I'll just jump directly into the description of the systems and the kinds of demos that we have planned for you. All right, so as Petros alluded to, there's two days of demos, but there's also two major themes that are related to those two demo days. The first theme for day number one is autonomous emergency landing, executed with a variety of systems and at different locations and very diverse types of environments that we are considering for those kinds of executions of emergency landing maneuvers. So the first type of system that we have planned to demonstrate is an amphibious system. The idea here is to have a system that's capable of sustaining even being submerged in water, so that we can have repeated testing with that kind of capability. Of course, the system is not designed to just execute emergency landing, but it's one of the possible situations where we can test this kind of capability of detecting water bodies that can lend themselves as potential opportunistic targets for doing emergency landing maneuvers and safely landing on them. So to give you a little bit more detail about this particular type of system, it's a system that's amphibious and self-sustainable at the same time. It's been developed in order to possess the capability to be out there in the wild and harvest solar power in situ, such that it can remain charged and do cell hibernation cycles, so that it can do back-to-back missions in a self-sustained manner without any kind of human supervision needing to be around that. It's built to have the amphibious capabilities that are necessary in order to do that. So there's a watertight container that has been custom designed and exhaustively tested to host all the electronics and the battery systems and everything that's on board. That's equipment that that we do not want to have exposed to water. And of course, there's all sorts of questions regarding heat dissipation and all that stuff. That's also part of the design that is currently hosted. There's a waterproof camera system, USB camera system that's on board in order to do basic data collection in a way that allows the vehicle to have some sort of perception capability that's vision-based. And the high-level autonomy stack is based on Ubuntu, ROS, and deployed on an ARM-based architecture that has a neural processing unit. What's the reason for having a neural processing unit? It's, of course, to be able to do learning-based pipeline execution. And the reason why we have used this, as you're going to see in the next video, is and by the way, this video is a demonstration of the type of mission profile that you can expect to see during these tests, starting with the vehicle submerged in water, and then just to facilitate a very easy, smooth takeoff. And then starting a mission that's a survey mission. What you see in this video specifically is that the neural processing unit on board is capable of detecting the environmental critical phenomena. For example, this wildfire that is detected in the very first section of the video. This is a different application of deep learning capabilities, but it is still relevant to autonomous systems with this kind of degree of deep learning driven perception, AI driven perception. So this particular system, as mentioned, is capable of doing self-sustained operation over multiple days, where it's does self-hibernation overnight or during periods of power scarcity, and then it recharges and then takes off and does back-to-back missions. That's the design, but of course, facilitating emergency landing situations and testing where it has to land on a water body. It's a natural capability that is offered by this type of vehicle. So I won't spend any more time on this video because you pretty much got the idea. This is the same lake that we will be doing our testing. So you'll be able to see it from up close. Hopefully it will be not too windy and calm conditions and all that stuff. May is not the easiest month for Reno, which is known to have weird weather sometimes, but hopefully it's going to be a good couple of days for you to experience this kind of field test out in the field. The second set of videos, these are things that we have shown also in the past, but this is essentially what drives the basic functionality that we want to have tested. It's the deep learning detection driven landing zone or landing spot or any kind of object of interest that can lend itself for landing type of operation. The first video on the left is a basic YOLO detection, bounding box based of terrain landmarks that can be chosen as potential safe landing targets. The second one on the right is again a basic YOLO detector based operation where we are detecting another robot that we have marsupial deployment. And it is a known target for the two robots to assemble with one another, and this is again driven by a deep learned framework of having learned essentially to detect a spot robot from the air. These two, however, do not correspond to the much more difficult task of detecting water bodies that do not have such a clear, distinct outline. It's different detecting a parking lot, it's pretty much a square. It's different detecting a small robot, like the spot robot, it's pretty much a square also. So we need something that's a segmentation-based framework executed online in order to be able to detect classes like large bodies of water. So the first field experiment with this amphibious robot is, as I mentioned, opportunistically detecting a local water body real-time onboard perception, and simulating at some point a fault condition during a survey mission, and having the vehicle just figure out where is the best location to conduct landing. And of course, if the water body has actually been detected in the local area, it is one of the considered possibilities. In this particular example, it is pretty much the best possibility for landing, given its amphibious nature as well. So it's a segmentation deep learned framework that we are executing. There is a quantization scheme in order to make it manageable to be deployed on board the neural processing unit of the small onboard computer that we are flying on the aircraft. Again, remember, this is a small aircraft, and it needs to also be small in terms of power footprint, both for reasons of prolonging the endurance of the operation, but also for reasons that have to do with heat dissipation inside the watertight container and all that stuff. So we need a smaller computer, pretty much, to be able to execute those kinds of capabilities as well. So what you see is, at the bottom left, is the original, let's say, planned mission. So this is a survey mission of the aircraft around the lake. This is the original planned mission, which means that if the whole scheme is successful during real-time execution, we shouldn't see this mission. We should see the mission at some point interrupted and a vehicle cutting through to some point into the lake in order to do emergency landing into the lake bed, as it has been previously detected through the YOLO segmentation framework that is trained, that we have trained to be able to detect large water bodies, as an instance like the one that you see on the set of images on the right, where you can see the original lake bed image and, of course, a segmented part of it of the lake. So again, we will go over all those things in the field, explaining what we are seeing, but the expectation is to see a mission that is not concluded normally due to the simulated fault condition that will happen on a timer basis sometime during the execution of the mission. We will see the vehicle taking a decision through this opportunistic framework of detecting this safe landing zone, being the lake bed, in an autonomous manner on board the aircraft. Continuing down the same vein of the day one theme, which is the autonomous emergency landing, we will also are also planning to have a test with a much larger system. This is a system owned by SNC. It's the Volley 10. It's previously a Volance system. Volance has been acquired by SNC, so it's not their system. This is a much larger system, close to 10 feet of wingspan, larger payloads, close to 90 minutes of flight, and it's capable of carrying a full and native NVIDIA onboard computer, which means NVIDIA Ampere GPU with 1024 CUDA cores, 32 tensor cores. It's what you would expect to just deploy a neural network in the easiest fashion possible and have it executed as fast as possible as well. So pretty much a very different situation than having to quantize a network in order to deploy it on a small neural processing unit on board. At the same time, it's capable of supporting much larger payload configurations. So what you see here is the sensor payload that they have designed for the system, and they are flying, which consists of 4 electro-optical cameras and VN200 vector nav GNSS INS solution. Pretty high quality stuff, high-end equipment being flown on this particular system. What's the goal here? The goal is to be able to demonstrate similar capabilities with a full-scale footprint system in the field. So the planned type of operation here is again a similar type of operation where the landing zone in this situation is a small field, sports field. I think it's a baseball bat field, something like that. You can see it in the, this is a Google Earth image on the top right that you're seeing. You can pretty distinctly tell which is a good landing zone in this type of environment by seeing that there's this green patch, which is that particular field, playground, whatever you want to call it, in the center of the image. So this is what a human pilot would see. It would be a good indication of a safe landing zone, assuming there are no people, and there aren't going to be any people on that day. Assuming that you have to have a bird's eye view of the entire landscape and pick a place where you know that it's going to be the best case scenario for you to conduct landing. So the same thing here, done autonomously. That's the purpose of the test. Again, this is a segmentation framework that's running online. You can see some instances of segmenting out that particular field in the images that are collected by a quadrotor drone. This is a drone that supported the data set collection for us to be able to do training and validation and all those things that we need to do with those types of frameworks. This is the framework that's going to eventually be deployed on board and the volley system and tested in the field. The location is in California, Doyle, which is about 30 minutes further up north from the location that we plan to do the Silver Lake test, the test that I was talking about before with the amphibious system. So those two tests are going to take place back to back. And it's consistent with the fact that we are showcasing the same thing of emergency landing on the same day. Again, here, simulated fault condition. We're not going to inject a real fault in a system. We are just going to ask it to do something about a fault that is assumed to be as significant as requiring the system to do as quick of a landing as possible. All right, that's it about the first day and the theme of emergency landing. The second day theme has to do with robust obstacle avoidance. For this type of test, we are planning to utilize the Minihawk system. Pretty much people in this project should be very well aware of the Minihawk system. It's a small-scale, rapidly prototypable system that carries lots of sensors. It's not the most capable in terms of flight performance. It has been called a flying brick, but it's small enough to facilitate very quick, very rapid testing in the field, which is why it has been good for us. And also, if you put it into fixed-wing flight modes, because it's a hybrid tilt rotor, it can also spend a little bit more time in the air by utilizing the fixed-wing aerodynamics. So the sensor suite is what you see: some odometry, visual inertial odometry sensor, GPS, regular cameras on board, all that stuff, and the common thing that ties it back to the first system that we saw is that it carries a small footprint onboard computer with a neural processing unit as well that is capable of executing at a reasonable performance, but also at a reasonable power energy footprint, some learning-based frameworks. So what we plan to do with this type of system is to show an integrated evaluation of executing covariance steering on board such a system in order to offer simulated obstacle avoidance during a landing zone approach maneuver with the safety guarantees that are ensured by this type of covariant steering framework. So the idea is that we have a certain landing zone trajectory that's been already pre-planned. It's been followed normally by the vehicle, and at some point it detects that there is a significant obstruction in the planned trajectory, and it has to replan a different type of trajectory that ensures that there is not going to be any kind of collision with the obstacle, but in a way that accounts also for the uncertainty and the planned uncertainty, the predicted uncertainty of the aircraft as it's going to keep moving. So essentially ensure that the covariance panel stays collision free during the execution. We're going to have more visualizations and more explanations in the field. What you're seeing right now is the type of simulation testing that we are running right now, utilizing the real flight environment for simulating the dynamics. This is just the flight dynamics. We're not going to do this test in an actual football field, soccer field. So the environment is irrelevant. The real flight simulator is just simulating the flight dynamics, and this is the execution of the integrated covariant steering on a software in the loop plus ROS-based computer that's running the framework and is just simulating the resulting behavior, and then we take it out in the field, which is a similar location as to the one that you're going to be seeing on the next day, where we fly the Mini-Hawk system. This is a different trajectory, but still it's a piecewise trajectory that's testing individual components of the whole framework, but it's still covariant steering integrated in real-time execution on board the Mini-Hawk platform. Of course, the final test that you're going to be seeing on day 2 is something that we are currently going through, so it's going to be also a small surprise to see how it works. We have students out there in the field today right now testing the whole switching behavior between different trajectories and doing the simulated obstacle avoidance and all that. But this gives you an idea of the kind of environment that you will see the vehicle operate under. And the combined operation will be something, again, to the extent of having a vehicle following a trajectory and then seeing it take a different path and doing a different maneuver than the original one, due to the fact that there is this simulated obstruction, and it has to avoid it by ensuring at the same time safety guarantees through steering of the covariance panel of the system, and still maintaining a smooth approach maneuver that ends up taking the system down to a safe to the original planned landing zone. That's all for the moment. We'll talk more in the demo days. We're looking forward to seeing you. I'd like to take any questions if you have any right now. Otherwise, thank you so much, and I'll turn it back to Petrus.
Thank you, Christos. This was awesome. So let's see if we have questions now from audience. So if no questions, I want just to clarify one more time, especially we have people from NASA's leadership team, that these demo days are meant to show both physical demos, like what Christos showed, also some simulator advancements, like what Cyan showed last time, how to integrate tools for real-time auto-coding verification and validation coming from Cyan's group. And also we will be coming to the demo days from Illinois with recorded movies from our Bicon lab, where we can fly small drones. We don't have here the fields and these opportunities to flight test real vehicles in open fields. But we have Bicon Lab where we are able to fly some innovative algorithms to do new type of hardware development that look pretty good and are very relevant to this project. So we will bring our recorded videos and we'll have Christos doing the real world demos and some simulators for real-time collision avoidance, for autocode verification and different types of semi-finished products that can be delivered to NASA upon completion of the project, so NASA's internal teams can take it from there and integrate with their other software suite and have more developments based on that. If no questions, we can meet in 2 weeks. So, okay.
Naira, can you hear me?
Yes, Christos.
Okay. Sorry, but I don't know why at the very end of the presentation right there, when I clicked stop share, my computer completely crashed. It's not the most unfortunate to have a computer crash, but at least the presentation was finished. So
Okay.
let me know if you have.
Sure. I mean, if there are no questions, we're right at the hour, we can close it.
So yeah, Nara, this is Petros and Christos. Everybody, thank you. This is great. Look forward to seeing you, everybody in person, and getting into details.
Okay, and one more last point, because today we cannot predict the weather in 2 weeks, so we are asking Christos to record all these videos that they are doing. You never know on that day what will happen, a rain, a storm, or whatever. We are in global warming, so that's why, as a backup plan, we'll have everything recorded. Of course, going to the sites and seeing everything in real time in action is a lot more exciting than watching videos. But we have to have a backup plan just in case. God
Great
forbid.
contingency management.
Right. Contingency management, exactly. Look forward to meeting you all. It has been a while. And I have another exciting news. I was able yesterday to watch the Lockheed Martin movies, for which they finally got public release. They were not able to show these movies in October review, but James will be coming and showing the Lockheed Martin flight test on the Vista 62, this F-16 model that has been refurnished with new capabilities to fly AI-type algorithms and be more ready for autonomous flight. So James will be bringing the Lockheed Martin movie for which he got public release. I'm all excited about that.
Yeah, that sure sounds exciting, Naira. Together with Christos' demo, I think it'll be a very complete set to show the capabilities. Yeah.
So we look forward to meeting each other. Thank you all for attending today's meeting. Okay, thank you.
Thanks.
Have a good weekend, everyone.
Good weekend. Thanks. Bye-bye.
Yeah. Bye-bye.
Bye-bye.
Bye, Naira. Bye-bye, Petrov.
Bye-bye.
Bye, Bye-bye.